Welcome back to Mathematics Lifeline. In today's video, I'd like to discuss L'Hopital's rule and explain why it's so useful and why so many students love it so much. So we're going to do probably 4 examples in this video, and they're going to be kind of increasing in difficulty, but L'Hopital's rule is so useful. So here is the statement of L'Hopital's rule. So I'm writing it as a theorem, and it says if the limit as x approaches a of f of x over g of x is an indeterminate form. Now, before we continue, I want to explain what that is. Indeterminate is 0 over 0 or infinity over infinity. That's it. That's the only time that we have an indeterminate form. But if that's the case, then the limit as x approaches a of f of x over g of x, so the original limit, is equal to the limit as x goes to a of the derivatives of the numerator and the denominator. So all we're taking here is the derivative of f of x, and we're putting that in the numerator, and the derivative of g of x and putting that in the denominator. So, this can obviously be proven. We're not going to do it in this video, but this is such a helpful trick when we're doing these limits because you don't have to use the algebraic methods to simplify some of these. Some of these you're going to, if you get 0 over 0 or infinity over infinity, often you can use L'Hopital's rule and it makes the process so much simpler. So without further ado, we're going to go ahead and get into these 4 examples, starting pretty easy, but you'll see how useful it is automatically. So we'll go ahead and start with the first example right now. Okay, so here we have example 1. So this one is the limit as x approaches infinity of 3x plus 7 over 4x plus 2. Now remember, the statement of L'Hopital's rule said it was the limit as x goes to a of f of x over g of x. So this right here is our f of x, and this one is our g of x, just to keep consistent with the definition that we presented. Now, if you were going to do this limit in the ways that you learned early on in your calculus class, you would need to either compare what these limits approximate at infinity, or you can divide all these terms by the highest degree. So I have a video out on this about the systematic versus the visual degree rule for limits at infinity. But you could divide every term here by an x and you would get your answer. But the nice thing about L'Hopital's rule is that we want to see what this gives us if we just plug in infinity, right? So if we plug in infinity, we're going to get 3 times infinity plus 7, which of course is still just going to be infinity. And then the bottom is 4 times infinity plus 2, which again is infinity. Now remember, infinity over infinity doesn't tell us anything. This is indeterminate. So because it's an indeterminate form, we're able to use L'Hopital's rule. So we want to denote that in some way. So I usually will denote it with just a L'Hopital's rule. That's kind of what that means right there, just to show your instructor that you're doing that step. But essentially what we do is we're going to take the derivative of the numerator and the denominator. So the limit stays the same. So we still have the limit as x goes to infinity. But we want to take the derivative of the numerator and the denominator now. So the derivative of 3x plus 7, we just take the derivative of the 3x, right? Because the 7 doesn't ultimately matter. So the derivative of 3x is going to just be 3. And the derivative of 4x plus 2 is just going to be 4. So this is now the limit as x goes to infinity of 3/4. Well, there's no x here. So this limit doesn't even matter. We're just going to get 3/4, right? So 3/4 is our answer. And we would get that by doing the systematic way of dividing by the highest degree. But you can see how much quicker this is. All we did was take a derivative of this and a derivative of this, and then we get our answer automatically. So the answer for this limit would be 3/4. So this is just kind of the first example of L'Hopital's rule, and you probably don't even see how powerful it is just yet. But this is very, very helpful, especially for more complicated limits. So we're going to get into a couple harder ones right now. So we're going to go ahead and get started with example number 2. Okay, so here we have example number 2. This one is the limit as x approaches 3 of x squared minus 9 over x minus 3. Now, you've probably seen this question before, or something very similar, right? If we were going to solve this using, it's typically chapter 2 that we're doing these limit laws. If we were going to solve this, we would need to factor the numerator, and we would cancel out an x minus 3 from the top and the bottom. But with L'Hopital's rule, we don't need to do that, and that's so great because it takes so much work away. But the first thing we always want to check before we try L'Hopital's rule is to make sure we get an indeterminate form. So if we plug in 3 here, we're going to get 3 squared, which is 9. 9 minus 9 is, of course, 0. And in the denominator, we have 3 minus 3. 3 minus 3 is also 0. So this is indeterminate, so we're good to use L'Hopital's rule. So we want to signify that. So we're going to write L'Hopital's rule. Now, your professor might tell you to do this different ways. There's some people use different notations. I will, like I said, I typically will use this. But now all we need to do is take the derivative of the numerator and the denominator. So we'll have the limit as x goes to 3. So we're going to take the derivative of x squared minus 9. Now again, this minus 9 doesn't matter, so it's just the derivative of x squared. And the derivative of x squared using the power rule is just going to be 2x. Now in the denominator, we have the derivative of x minus 3. And of course, the minus 3 doesn't matter, so it's just the derivative of x, and the derivative of x is 1. So what we're going to do is rewrite this as the limit as x goes to 3 of 2x over 1, which is just 2x. And now we see that we can plug in that 3 immediately into the x, right? Because this has no issues anymore. So we'll plug the 3 in and we'll get 2 times 3, which is equal to 6. And that is the answer for our limit. You can see how much quicker this is. All we did was just take the derivative of this, take the derivative of that, plug it in, and we get our answer. Right? Instead of having to remember how to factor x squared minus 9 and cancel it with the x minus 3, we can do this in one step. And it's very, very helpful. Okay, so that's it for example 2. We're going to go ahead and move on to example 3. Now, I want to showcase some harder examples, right? These first two have been pretty easy. Example 3 and 4 are going to be a little tougher, but you can see the power of this rule and how helpful it actually is. So we're going to go ahead and move on to example 3 right now. Okay, so here we have example number 3. This is the limit as x goes to 0 from the positive direction of minus x ln x. Now what we want to notice here is if we plug in 0 from the positive direction, we're going to get a 0 multiplied by a negative infinity. So this is not a form that we're really familiar with yet. We're not sure how to do this, but we can actually manipulate this to get it in the form of infinity over infinity. So the first thing that I want to point out to you is that minus x ln x is actually equal to ln x divided by negative 1 over x. Because if we're dividing by a fraction, remember we flip and multiply. So we would flip this fraction, which means that x would go into the numerator and we would have the negative x. So we'll have a negative x ln x. They're equal. So if we do that, we can rewrite this limit as the limit as x goes to 0 from the positive direction, and we're going to write it exactly like this. So we have ln of x over negative 1 over x. Now you might not immediately see why this is helpful, but let's think about ln x as x goes to 0 from the positive direction. We're actually going to get a negative infinity. If you look at the graph of ln x, you'll see that as it approaches 0 from the positive direction, it comes down to negative infinity. And the same thing for this one. When we plug in 0 in for x, remember that when we evaluate 1 over a really, really small number, that's going to approach infinity. But in this case, we have negative, so it's going to be negative infinity. And of course, that is equal to infinity over infinity, which that is an indeterminate form. And that is good because now we can work with this directly. So we're going to use, like I said, L'Hopital's rule, and we're going to take the derivative of the top and the bottom. So we're going to end up having the limit as x goes to 0 from the positive direction. Remember, the derivative of the natural log of x is going to be 1 over x. And the derivative of negative 1 over x, well, this is minus x to the minus 1. So the derivative is going to be x to the minus 2. So this is going to be 1 over x squared. So we can get rid of this now. So now we have the limit as x goes to 0 from the positive direction of 1 over x squared. Now we're dividing fractions, so we can flip and multiply. So this is the same thing as the limit as x goes to 0 from the positive direction of x squared over x, which of course we can simplify that just a little bit more. From the positive 0 from the positive direction, x squared over x is just x. So now we can directly plug in 0 and we will get 0. And that is the answer to our limit. Now, if you don't believe it, you can even graph this function. If we were to graph it, it actually will look like this, somewhat like that. So as x goes to 0 from the positive direction, you can see it approaches the origin. So this is where L'Hopital's rule gets tricky because this is not directly in the form that we had. However, this is. When we rewrite it like this, we can actually turn it into an infinity over infinity. So anytime you have like a 0 times negative infinity, 0 times positive infinity, always try to see if you can rewrite something in terms of a form that is indeterminate and a form that we know how to work with L'Hopital's rule. So yeah, that's it for example number 3. We're going to move on to the final example of this video, which is example number 4. Okay, so here's example number 4. This is the limit as x goes to infinity of 1 plus 1 over x, all to the x power. Now, what we're going to do is we're actually going to set up a function here. Now, this is a little bit of a trickier question. There's a few ways to do it. Some people will use what's called the two-step approach, but I think it's a little more intuitive just to set up a function. So we're going to say that y is equal to 1 plus 1 over x to the x power. And so when we try to do this limit, right, when we look at it from right here, this is actually going to be 1 plus 1 over infinity, right? 1 over infinity is just going to converge to 0. So we're going to have 1 to the infinity. Now, 1 to the infinity is another indeterminate form. Now, a lot of people are confused by that because you would think 1 times 1 times 1 times 1 is just going to keep giving you 1. But this is actually another indeterminate form, which is why we need to do this method that I'm going to show you. So if we have this function right here, we want to think about ways that we can get this x down into the front of the function, because the infinity in the exponent is the problem. So the way we're going to do that is we're going to take the natural log of both sides. So we're going to have ln y is equal to ln of 1 plus 1 over x to the x power. Now remember that if we have a power and the exponent in a natural log, we can pull that power down to the front. So we'll have ln y is equal to x ln of 1 plus 1 over x. Now, here's the way that this is actually going to work. We need to take the limit of this now. So we're going to look at the limit as x goes to infinity of x ln of 1 plus 1 over x. Now again, we need to look at what this gives us, right? When we plug in infinity here, we're going to get infinity. And when we plug in infinity here, we're going to get ln of 1. And ln of 1 is 0. So this is actually infinity times 0. So that means that just like the last question, we're going to want to rewrite this. So the way we're going to do that is we are going to rewrite it as the limit as x goes to infinity of ln of 1 plus 1 over x divided by 1 over x. Now when we do this, we're able to evaluate this because this becomes ln of 1, which is 0, and then this would become 0. So this is 0 over 0, so we can use L'Hopital's rule. That's what we're going to do. So we're going to take the derivative of the numerator and the derivative of the denominator. So we'll have the limit as x goes to infinity. So we have the derivative of the natural log of 1 plus 1 over x. So that's going to be 1 over 1 plus 1 over x multiplied by the derivative of 1 plus 1 over x, which actually turns out to be minus 1 over x squared. And then we're going to divide by, we have the derivative of 1 over x, which just like what we did in here, it's going to be a minus 1 over x squared. And now the nice thing here is that this and this will cancel out. So we really just have the limit as x goes to infinity of 1 over 1 plus 1 over x. And when x goes to infinity, this part will go to 0. So it's just going to be 1 over 1, which is 1. Now remember that we took the limit as x goes to infinity of this, and that was ln y. So we really want to solve for y here. So we have ln y is equal to 1. So we're going to exponentiate both sides. So when we do that, we get y equals e, which means that our final limit will converge to e. And that will be our answer for example number 4. Now I just want to point out that this right here is actually the definition of Euler's number e. So it's very cool that we can do this using L'Hopital's rule, because if we couldn't, this is a much harder way to, there's a much harder way to go about this. Again, you may not see it like this in your classes. This is the way that I was taught. In a lot of textbooks, it's called the two-step method. And you do the same thing, it's just not as, it's not as intuitive to me, I don't think. Because to me, every time I see an exponent that is as an x, I think to create a function and do it like this. But yeah, this is it for example 4, and this is it for the video on L'Hopital's rule. Now, if you have any questions, again, feel free to let me know. This is a pretty complicated topic, but it's so helpful. You know, these questions can get tough. They can look really challenging, but L'Hopital's rule is so useful in the long run, and you will learn to appreciate it. Trust me, even if you look back at the earlier part of your semester, learning calculus, you're going to see how many of these limits you could actually use this for and how helpful it is. But yeah, like I said, that's it for this video. If you have any questions, leave a comment. I try to answer as many as I can. But if not, then I will see you in the next video. Thanks for watching.